Okay, it started. Let me go to my share screen and chapter 24. Can y'all see the slideshow?
Yes, sir.
Okay, good. I'll get it on the current slide. And now I'm going to move around some things that are blocking. This taskbar is definitely in the way, so I'll move it as far out of the way as possible. And Valerie's a little bit in the way, not too bad. Let me scoot you over some. Okay. Okay. Now before we pick up where we left off before, let me go over a few things. Now, I don't know, have y'all been checking your emails fairly regularly?
I have.
Okay. Did you see an email from the dean about student course evaluation? Huh?
About the survey?
Yes.
Yes, sir, I did.
Okay. When was that? Yesterday or day before?
I think it was the day before.
Yeah, that's what I was thinking too. I mean, how late in the term do you need to wait until you put those out there for students to do? So, and now I've got only 3 people here to make the announcement for. Okay. So I'm making it here. So if they do listen to the last class on YouTube videos, they'll know. I'm also going to take that email and put it on Blackboard Message. However, that Blackboard Message has so much stuff in it, I'm not sure anyone goes back and checks to say, hey, this wasn't there before. I know you'll do it for tests and labs, but something like that, I'm not sure. So I just want to say, please do the student course evaluations. By the way, have any of you done them already?
I have.
Oh, excellent. How long? Oh, from the previous semester?
Yes, sir.
Okay, yeah, but not for this semester?
Not this semester.
Okay. Do you remember approximately how long it took you to do one?
Oh my God,
That's all right.
not long.
Not long at all. Probably 5 to 15 minutes, I'm guessing. Okay. So please, it doesn't take long. We value them. So please, please do the student course evaluations. Okay. Then let me go over how we're going to wrap up the term. Now, this morning I had 2.5 hours or so of time that I could be in the office before I had to start getting ready for my first class. Now, I didn't do all these, but this is largely, a good portion of these came in this morning. Okay, I still have some out there I haven't printed yet. I could see them out there, but I ran out of time. So I've still got printing to do, and then I've got all that grading to do. And then I've got to put it on Blackboard. Okay, so miles to go before I sleep. Okay, but there are promises I will keep, that I will get these graded. I'll get them out there on Blackboard. I just can't say when. Okay, as soon as I possibly can. I did catch up on printing, but the papers were coming in so fast I could hardly catch up any of the old stuff because new stuff was coming in constantly. And I know there's more new stuff out there while I've been teaching today. So I'll be printing like crazy most of the evening probably, and then at some point, probably tomorrow, I'll finally get a chance to start grading. But if not, Friday we'll be doing nothing but, almost nothing but grading. Printing probably some more things, but then grading. And then as soon as I get the grades done, all those stacks done, I'll be putting grades on Blackboard. When I get that done, then I'll be ready for the other. So what are we going to be doing? Today we finished chapter 24. We'll do the chapter 24 lab that a couple of you have already printed off. Okay? Now, it's going to be a very easy lab, a very quick lab. Okay? And like I said, because at least one of you doesn't have a book, and possibly others in the class don't have books, I will go back through the slide set to show you the things you need to know to get the lab. Since you don't have books, I'll show you on the slide set. If there's anything that's a lab question that's not on the slideshow, I'll let y'all work among yourselves to remember that from your notes and stuff, but I think it's all out there. Okay, so once we finish the lab and we check out for today, then I will put out your chapter 24 test. That is ready. Okay, I checked on that this morning and it is ready, and then I'll put out the final exam. Okay, I checked on that and it is also ready. So actually the lab was the thing that took the longest because I had to go from WordPerfect to PDF. So we'll go with that then. And when y'all printed it, I bet you it showed up sideways, but y'all were able to turn your paper, right?
Yeah.
Okay, did it show up sideways? That's all right. That's okay. I was just wondering. Okay. Okay. Yeah. Okay. I just wanted to make sure because I knew some of you might want to type directly onto the screen if you had that capability. Sorry, I didn't get it turned before I was in such a hurry to do it. I just did it the way it came in. So anyway, we'll go from there. Any questions on how we're going to proceed?
No, sir.
Okay. So here's where we left off last time. We're in chapter 24, which covers Earth's waters, is the title of it. And we got most of it covered last time. And just a quick review of what we've done so far. 4.1 was water on the Earth, and we looked at fresh water. We looked at in freshwater, surface water, and groundwater. We looked at freshwater as a resource, and then that was 24.1. 24.2 is seawater. That's where we are now. We looked at the oceans and the seas, the nature of seawater, and we're starting today on the movement of seawater. And that's where we are. If you have your books, that's page 620 if you have the big full book. If you just have the miniature book, that's on 24-15. Now, before I do much more pick up with this current slide, let me mention the top of page 2415, and that's on estuary pollution. I don't know if you can see this in the window. It's probably not good enough for you to read, but that is a really, really good blurb. Okay? Now, number one, what in the world is an estuary? It's basically the area where, say, a river comes into a bay or something like that. It's kind of the interface between freshwater and saltwater, okay, where the two meet. Freshwater coming in, dumping into the saltwater. Maybe a little further upstream where it's a little bit fresher, but the water begins being somewhat brackish. Well, unfortunately, our history has been, we have been doing a terrible job for most of our history as a country of polluting our freshwater sources. Okay? Now, somewhere back in I'm guessing around the 1970s or so, finally the federal government took a real serious look at this and started and passed, I think, the Clean Water Act. I don't remember exactly when it was done, but just to give you an idea, Lake Erie, one of the Great Lakes, the 5 Great Lakes in the northern and northeastern U.S., okay, 5 huge, wonderful, beautiful lakes there. Lake Erie was almost completely dead. There was hardly any fish life in it, and nobody dared eat anything coming out of it. It was so terribly polluted. We were doing the same thing for most of our rivers. Industry was dumping whatever they wanted to in it. Cities and towns were dumping whatever they wanted to in it, and you can imagine what that was, part of it anyway. We were just messing up big time. So over the years, we've been doing better. I think, I'm not sure, but I think you can probably eat the fish out of Lake Erie again. It's come back to life, and I think the life is sustainable. Okay, I don't think there's enough pollution in it to make it hazardous to health. I can't swear to that, but I believe that's right. But still, There's so much upstream in our rivers, and we treat our water as if it's ours to use and abuse. And unfortunately, we've been doing that. Okay? So that's what they mean by estuary pollution. All that's collected on the rivers from all the watersheds leading into that river, that gets collected and dumps into the estuaries, and they can become really badly polluted. Let me mention just a couple. Chesapeake Bay, that's very close to the nation's capital, Washington, D.C. It has had before, I don't know if it still has it now, some really serious, I think what they call red algae or red sea. It's because of the pollution there. Algae have been growing there in just incredible numbers and basically choking off the oxygen supply, and that's killing the fish. And there's all sorts of things like that happening, different variations on the theme. So even though the Clean Water Act has been in play for probably 30 years, 40 years or so, it hasn't cured everything. So anyway, that's a really good read on estuary pollution. It goes into far more than what I just said, and in a much better way than I just said it. So let's move on to seawater, or the movement of seawater. Now this is I don't know how they figured this, but I guess somehow the models come up with it. The mixing time for Earth's seawater. They figure you have a complete mixing of seawater about every 2,000 years. That means every drop of water that's in the, this is an exaggeration probably, every drop of water in the Atlantic 2,000 years ago could have easily been in the Pacific or in the Indian Ocean or somewhere on land or somewhere in a sea or somewhere else. There's been a complete mixing about every 2,000 years, which when you figure the Earth has been pretty much the same shape it was, is now about 3 billion years at least. That means about 1.5 million complete mixings over those 3 billion years. So that means that there's a good chance that some water that was in some dinosaur some many million of years ago, you probably got that a drop or two of that water in your body, okay? Or you have had sometime in the past, or you will have sometime in the future, because all the water has been mixed 1.5 million times over 3 billion years. Now, what does the mixing? There's two types of motion that are the primary mixers, okay? The first is waves. If you've ever been to the beach, you know the waves are always coming in. Always coming in. They always will come in. Now these are produced by disturbances. What disturbances? Well, there's wind disturbance. That's what creates most waves. Okay? However, when you have things like underground earthquakes, which is, underwater earthquakes, let me put it that way. All earthquakes are underground. Underwater earthquakes, then they create tidal waves that do pretty big disturbances, way bigger than normal waves. Okay, so those are waves. Now that mixing is largely in the upper part of water, of the ocean's waters. It doesn't go that far deep. The deeper waters are mixed by currents. Currents are movement of water from one place to another. These can be very deep and they can be close to the surface as well. But they're not right on the surface like waves. They may be on the surface, but they may go much deeper than waves go. So let's look at these separately. If I can get the screen to advance. There we go. Let's first look at waves. Waves are the simplest structures. They're moving crests and troughs. Crest and trough. Okay? The crests are the high parts, the troughs are the low parts. There's three characteristics of these waves, And we'll be using some of these in later things we're talking about. Let's get the visual up there as well. Okay. First, we have what they call the wave height. The wave height is the distance between the bottom of the trough, that's the lowest part of the wave, and the top of the crest, the upper part of the wave. That's your wave height. And that's measured in a length measure. You can measure it in inches, feet, meters, yards, centimeters, whatever. That is a wave height. Okay? A wavelength is also a length, but that's from one crest to the next crest. That's how we usually measure. It could be from the very lowest point in one trough to the very lowest point in another trough. It's going to be the same thing because the waves are pretty regular coming in. Easiest way to measure is from crest to crest. That's called the wavelength. It's also, now the wave height is a vertical distance from trough to crest. The wavelength is the horizontal distance between two consecutive crests or troughs or any other like part of a wave. Now, both of those are length measurements, of course. Wave period is the time between the passage of two successive crests. Remember, waves are always in motion. So if you fixed a point right here and you had a crest come by, you started the clock right when that crest passed and wait for the next crest to come along, that would be the wave period. That's a time measurement, not a distance measurement. The time between the passage of two successive crests at some fixed point. Okay? Fairly simple concepts. Just remember, wave height, wavelength are both length measurements. Wave period is a time measurement. Okay. Now, most of your ocean waves, and by the way, we've now moved over to page 2416. If you've got the big book, that's 621. The figure we just saw is on that page. But the ocean waves basically, most of the time, come from the wind. The characteristic depends on three factors that have to do with the wind. The first is the wind speed. Certainly the faster the wind's blowing, generally the higher the wave, the greater the wave height. Okay? Now, why is that? If you had the first half of the book when they talked about energy, there are two basic types of energy. One is kinetic energy and one is potential energy. Wind is moving, so that's kinetic energy. Kinetic energy is 1/2 the mass times the velocity squared. So that's why wind speed is so important, because the velocity squared. You double the speed, you're 4 times the energy that's involved, 4 times the work that it's doing. So wind speed is a very big contributor to your wave structure. Okay? Now the second is the length of time that the wind blows. Okay? If you have a strong wind come up all of a sudden, that's going to produce a lot of little ripples very, very rapidly. But if that wind, even though it may not be as strong, is blowing across the surface of the ocean for a long period of time, it's going to build and build and build your waves, and not just the waves, something related to waves, your swells. And we'll talk about the difference of those later. So the length of time that the wind blows. See, even if it's a very strong wind for a very short time, then comes from a different direction, the waves get all mixed up. So, but if it's a long time from the same direction, then that's going to contribute to probably your wave length. Okay, could also contribute to wave height. Okay, the third, that's the fetch. Now that's not what you tell your dog, Roy. Same word, but it's the distance that the wind blows across the open ocean. Now think about the Pacific. The Pacific is a lot of ocean out there, and if that wind has been blowing over a long fetch, a long period, that wind going in the same direction, then that's going to contribute to wavelength and probably wave height. Okay, which of course, the longer the wavelength, probably the longer the wave period as well, to be crest to crest. So when I say length, that also affects the period. So it's the distance the wind blows across the open ocean. Very similar to what we have on land. If you think about the prairies out in the Midwest that are basically flat, if the wind blows in the same direction over a long time there, I mean, that can build up. But then when you get hills in the way, trees in the ways and stuff, then your wind gets dissipated some. Okay? Well, same thing, same type principle here. Now, I was saying how they could do, but it's a really complicated mixture of wavelengths and wave heights are generated because of varying wind speeds, varying length of time that the wind blows, and varying fetch over which the wind blows. So if all those are changing almost constantly and instantaneously, you really get a complicated mixture of wavelengths and heights generated. Now, smaller waves dissipate from friction within water. Wait a minute, does water have friction? Yes, it does. I don't know if you have ever swum in a swimming pool and decided to jump off the diving board, but you didn't make a very good dive and you happen to land flat on your stomach. When I was growing up, they called those belly busters. If you've ever experienced one, you realize water has friction. Okay, they hurt. They hurt really badly. Okay, because water doesn't, it sticks to each other like crazy. Okay, the water molecules. So smaller waves will dissipate from friction within water. Larger waves will too, but it just takes them longer time to dissipate. Smaller waves dissipate fairly quickly. The larger waves typically last longer, they typically travel faster, and they eventually coalesce, and this is what I was talking about, into a swell. Okay. Now, I think I've mentioned a few times before, I was in the Navy. I was on ships in the Navy, and I stood watch on the bridge, in the Navy. And usually, at least once an evening, we had to make a report to the captain on what current conditions were. And that usually included wave direction. Sometimes we estimated height, wave height as well, but usually direction, but also the swell direction. And sometimes they weren't from the same thing. A recent wind could create waves. A long time ago wind could have created a swell coming from a different direction. So the swells are the gradual long-term effects. The waves are usually shorter term and more temporary. Okay, so larger waves last longer, travel faster, and if they come from the same direction long enough, eventually coalesce into a swell. Then when the wind changes, it starts making new waves, but that old swell still abides. Pretty much the way it was until gradually it will dissipate. All right, so let's talk about the swells. They carry energy but do not transport water. Now the waves do a little bit of water transport as well. Mostly they're doing energy. But what the swells do, they basically, the same water just goes up and down. The swell comes along, raises the water. The swell moves on, that water sinks. The next water is raised. So it doesn't really transport water, but it does carry energy through the water. So if you think back at what this section was first started, movement of seawater, the swells don't really move the seawater much except up and down. They don't move it from one place to the other. Waves can, but the swells typically do not. Okay? Now, the individual particle motions, I said that's up and down. Really, it is moved a little bit forward, but then it moves a little bit back. So basically, the up and down with the back and forth produce somewhat circular motion. Now, here's an interesting phenomena. The diameter, that's the length across that circle, is equal to the wave height. Now let's go back and look at the wave height again. There's the wave height. And if you superimposed on that, I'm going to try to do this. I don't know if it'll work well or not. My drawing is usually not very good. But let me see if I can find it. Yeah, there it is. Okay. If you imagine drawing a circle, and I don't draw circles well, but if you drew a circle about like that, that basically describes the movement of the water, of a particle of water. Near circular with the diameter is the wave height. Okay? You'll see a picture in the text later that does a lot better job of describing it, but that's what we mean, the diameter. Okay, but the water just basically goes in a circular motion. When that swell first comes up, or the wave first comes up, it lifts it, so that would be going from the trough, here, so that's where it would start, and then the wave comes on, it lifts it up, and then when it reaches the peak, that same particle of water then is at the top here, right about where it was to begin with, except higher up, and then as the wave moves on, the water falls back down again. Okay, so that's what gives it that circular type motion. Okay, now what is a whitecap? That's formed when the top of a swell or wave, okay, is toppled by a strong wind. That's why when you see white tops, you know you got a pretty powerful wind out there. When you don't have very much wind, the swells and the waves, you don't really see any white foaming at the top at all. Okay. Here's that picture I was trying to think of. I didn't have to draw it after all. This is that, I forget, I need my pad in my lap to do this. This is that movement of a particle of water. Okay, if you can think of water like that, it moves in sort of a circular fashion with the diameter of the circle that's from one end to the other exactly a wave height, or very close to it. Now, a little bit deeper, you still get that motion, but it's circular motion, so you're not really transporting the water much at all. Some of it's getting lifted up, some of it's falling down, but as it's lifted up and falling down, it moves somewhat right to left, but basically stays where it is. A little bit deeper, and you have a little bit smaller circle. Okay, now this is somewhat interesting. About one wavelength, which this is a weird juxtaposition of these characters. One wavelength, which has nothing to do with up and down motion, one wavelength down there, you're going to, let's see, let me put it that way. That's one wavelength down. Half of wavelength would be right around here, and at that point, I don't know why they put it down here, but at that point you get basically no more motion. No circular motion. The water's just doing whatever it was going to do. Sitting still, moving in a current, whatever it was doing, it's going to do here, not affected by the wave at all. So basically, your water mixing only mixes in the surface by waves and swells in about 1/2 wavelength down. So a longer wavelength, you'll have deeper mixing. Shorter wavelengths, not very much mixing. So I don't know why they brought that up. It is an interesting phenomenon, but they don't really do much with it. Okay. Now, that's if you were out in the open ocean. But most of the time we see the water and the waves coming in from the shore or short distance from the shore. And there's a couple phenomenon or effects that the shore interacts with those waves and or swells. Okay? And one of these is called refraction. Okay? Actually, I think I'll put this aside and use my cursor here. Okay, refraction. And what that means, refraction basically means bending. The shoreward side of the wave slows down first, and meaning the part that was further out to sea travels a little bit more, and therefore the wave front bends toward the shore. Let's see if they've got a picture showing that. They really don't show it well here, but they do show something from the previous slide. These are the deep water waves, and if you went further out, these things would be almost on top of each other. Okay, deep water waves, you don't see any white caps usually to speak of unless you have some very strong wind, as in really big storms, that type of thing. And you see that breakdown here. So 1/2 wavelength from about mid-wave down. After that, there's no movement, none of that circular movement. At the very top, you get a 1 wave height diameter, and then they diminish as they go down until you get about 1/2 wavelength down, and that's where the motion stops. Okay, but when you come over land, you start coming up to shore. Now you have two things going on. You have more friction with the bottom of the ocean. See, the bottom down here, the sea bottom was way below where any of the motion is happening. Up here, the motion is happening, so that distorts it. And now those circles get bent like this, okay? And then you have the second thing of the waves coming into shore, hitting the shore, and then they have to go somewhere, so they run back down. Now, if I were drawing these two arrows, I would have put the one going back on bottom and the one going top toward the shore on top. I don't know why they did them this way, but basically you do have a lot of mixing that way. Okay, and because you have the undercurrent here shown by that arrow that you have here, you have two things going on. The swells and the waves are coming in just like they were, but now beneath that, the water that's from the previous swells and waves are moving back, and that undercuts it and creates the crest breaking, and they call that the breakers, surf zone breakers, and that's where the surfers like to get on. So they haven't really shown a good picture of refraction yet. Let me see if I can find one in the book. Lo and behold, they don't really have. Oh yeah. No, they don't really. I don't know why they don't show refraction more, a better picture of it. But basically, now picture that. If this is the shoreline, but the wave front's coming in this way, then this is going to hit the shore first, and that bends the waves. Okay? It bends the wave, and that's what we mean by diffraction. That's a really terrible way to describe it, but that's what's happening. Now, your breakers, they are shown here at depths less than the wave height. Depths less than the wave height. So here's the wave height from trough to crest, and if you're at a depth less than this, the lower part slows, the top part breaks forward, and you get the surf, which is the breaker formation zone. Okay? Now, the taller the wave, of course, greater the wave height, these breakers are going to happen in deeper water. That's why places like Hawaii, where the waves, there's a huge fetch there, long area those waves are coming in. They've really built up a lot of energy, so they have pretty good height. Especially, I think the North Shore of Hawaii is quite famous for this, and that's where the waves break really, really high. Okay, and the surfers love it. I've never been there or seen it, but I've seen pictures of it. Now, the water is transported toward the shore. The water that is transported toward the shore by the breakers must return, and that's what creates the undertow. That's what I was talking about before, the water that's flowing back under. Now, this direct return of the water under the breakers, that's what undertow is. Now, you also have what they call longshore currents. This is motion parallel to the shore, and that produces other things called riptides once you enter a channel. Now, they're putting an awful lot there in a very short time. Now, my wife's family, I think I've mentioned this several times, years before I was in the family and several years after I was in the family, they love going to the beach. In fact, my wife said when they were growing up, they went to the beach every summer. But then once they got active in school and things like this, sometimes they couldn't do it as much. And then once they got out and on their own, they couldn't afford to do it as much. But once we were married, they went every 3 or 4 years, it seemed like, to the beach. So I would try to. I don't really enjoy the beach that much. I mean, I like it. I like seeing the water. I like things about it. But just to get out there and get burned by the sun, I don't care for it that much. But anyway, I'd go out there and try to do what they call body surfing. It was fun. If you ever caught a wave well and carried you in, sometimes it would grind you into the beach if you didn't stop it in time. But it was sort of fun. I would go out and do that, and sometimes do it for quite a while. But then I'd get out of the water and I look around and I had no clue where I was. Why? These longshore currents, where those waves have come in not parallel to the beach but at an angle, the longshore currents then are motion parallel to the shore. And while I was doing my body surfing, I didn't realize, but every time I did, it was taking me further down the beach. And sometimes I'd have to walk maybe half a mile back up the beach trying to find where I'd gotten in the water the first time. I don't know if y'all have ever noticed that, if you've ever been to the beach, but those longshore currents can make you drift down the beach. You better be able to figure out which way they're going, or else you're going to walk the wrong way. You'll be even further from home. But usually you can figure that out. Okay, now, what they're talking about riptides, those are, the undertow, that can, and if you have a lot of rough water, stormy type conditions, a lot of energy behind them, the wave heights are pretty tall, then they're carrying a lot of water up there, so you have a large undertow. And this happened to me in Virginia Beach, Virginia. I was up there with my cousin's family when I was in the Navy there, and we probably shouldn't have been out, but we were trying to take advantage of the weekend. But it was pretty stormy and rough conditions, and I found that undertow was dragging me away from shore, even though I was trying to get toward the shore. And I wasn't a very strong swimmer, and thank goodness my cousin's husband was. He helped me get out of that undertow and make my way back. I don't even want to think about what it would have been like if he hadn't been there. Okay, now, and it may be that I was affected also by riptide. What that is, the longshore currents are making you drift parallel to the shore, but then if you hit a channel, and the channel could be underwater and you don't see that, then the longshore current's carrying you this way, the channel is carrying you this way. Now you get pulled in two directions and can really get sucked under. Those are called the riptides. Produces riptides, the longshore currents produce riptides when you enter a channel, a deep place in the floor of the ocean. You can't tell it's a deep place, it's just out there. Okay. Now, There's a picture similar to the one on page 2417 or 622 if you've got that one. Neither one of these are all that good, but what you can see is a little bit of that refraction, I'm sorry. See here, that wavefront is close to the beach. Out here, it's further away. That's just a very small illustration of that refraction. That's the bending toward the shore. The wavefront bends toward the shore. Because it's coming from one direction, the shore is lined up in a different direction. Now, my best guess here, you could have an underground channel here and here because the breakers aren't as big in these two places as they are here and here. They don't go for as long. So that's an indication. And then you also, it's backed up with the discolorations you see here, indicating there's something else going on underneath the surface you don't see. But you see you can see that wavefront right there. You can see the next wavefront here, the next wavefront here, the next one there, and somewhere back there is another one. They're fairly evenly spaced here, but as you get close to the shore, that's where the refraction happens. So that's a semi-good shot. It seems like they could have gotten a better one than that, but that at least shows some of these features. Okay, those would be the areas I would fear being a riptide possibly in. The longshore current is going to make you drift parallel to shore down this way if you're not careful and watching. Okay, now this is an illustration. This, I think, is in your text. Now, that's before I go there. On your page 2418 or 623 if you have a big book, there are a couple of examples which basically are just sort of making up numbers and stuff and giving you an idea of how they do some of these calculations. They didn't give you enough information to do it, but they're showing you in this. And by the way, the wavelength, the symbol for that is lambda. That's a Greek symbol for that corresponds to our letter L. I don't know if you can see it in the book. Yuck. I can't get close enough to the camera to tell. Isn't it right above? Yeah, right above that example, right, you see that line in between the blue and the example, that middle line right at the end of that line, there's that symbol lambda. Okay, it looks like a stick horse or something like that. Yeah, I don't know how to say it. Okay, but before I do, that example there's two examples there. You can play with that if you want to. Now, there's another thing at the top of that page called rogue waves. Okay, these are usually unusually strong waves. There's this thing of it. Yeah, I know you can't read it from there, but that's where I'm talking about, top of the page there. Now, I don't know if this is true or not, but I've heard it several times that about once every 7 waves or so, you'll get one that's bigger than the others. I don't know if that's what they're talking about, these rogue waves, but you know, things will be pretty calm and gentle and stuff like this, easy to play with, and all of a sudden this monster just slaps you down. Okay, it's a much bigger wave, something to do with the frequency, with the resonance, with something like this that will create these big rogue waves. Okay, now this is illustrating what I was talking about before. Here the beach is not even, okay, and they've done a sort of a poor job here. If you went far enough out to sea, all of these waves fronts would be parallel, okay, but because the beach is not along the same line as that, they come in and bend. Now these are not quite the bending refraction they were talking about, but the longshore currents are the ones that make you drift down the beach like this. And if they hit a place, and the thing here, I found this a little backwards. They show a mound here, but then they indicate there's a channel here. Usually the channels would come in a place like this or like this, you know, not where there's a mound here. You wouldn't expect to see a channel, but if that longshore current happened to hit upon an entrance of a channel, then that could create the rip current carrying you this way. And they can be literally deadly. They certainly can be strong, okay? And if you go to the beach, be careful for those and listen to the people who know, because they follow that kind of stuff. So those are the shore effects that happen to these waves coming in, long period of waves. Now, I believe I mentioned this to you a few chapters ago. I think it was on our chapter on earthquakes in our book. That's where they talked about tsunamis. And I said on the slideshow a couple of editions ago, they put tsunamis in chapter 24. So that's where they show up here. We've already talked about them. You've read about them, but these are ocean waves created by earthquakes. Remember, ocean waves are created by disturbances. Wind is a certain disturbance, but it's not got that much energy because it doesn't have that much mass. Tsunamis, though, caused by earthquakes, enormous amounts of energy. And that's what a tsunami is. It's actually from a Japanese word, tsunami. They can be the largest of your ocean waves, and you don't want to be caught in a tsunami. Here are some of their physical characteristics, and this, to me, is absolutely unbelievable. The speed of a tsunami, that's the speed at which that wave is coming in to shore or just moving over the open ocean, can get as high as 70, or at least approaching 700 kilometers per hour, which, by the way, is about 420 miles per hour. That's the speed that it moves. Hey, if that's coming in, you're not going to get out of its way. There's no boat, there's no ship, there's nothing that can go that fast. Airplanes can, but they aren't in the water. Okay, if you're in the water, you're hurting. Okay, now the wavelengths. Can you imagine this? From crest to crest, 200 kilometers. That is about 120 miles from one tsunami crest to another tsunami crest. Okay, 200 kilometers, about 120 miles. But guess what? Traveling at 420 miles per hour, hey, it's not going to take long before that next one gets there. Now, the wave heights can be up to half a meter, which is basically your from elbow to fingertip is about 18 inches. Add a little bit to that, a couple inches of that, and you've got half a meter. So a little bit more than elbow to fingertip. That could be it on the open ocean, but it could reach in shallow water once it gets up to shore and it starts building like that, up to 8 meters. Now, what's 8 meters? I'm about 2 meters tall. This room behind me here, that would be about 3 meters tall. 8 meters would be almost 3-story building. If you're on the shore when a tsunami is coming in at 420 miles per hour and the wave could be as high, almost as high as a 3-story building, guess what? You're not in a good place. Not at all in a good place. You could get pummeled, and people have been pummeled. I don't know if you remember, I'm guessing it was about 8 to 10 years ago, there was an earthquake in Indonesia, underwater earthquake. It created a tsunami, that went across the Indian Ocean and hit a city on the other side. Uh, it used to be called Madras. When the Indian Hindu nationalists came into power, they changed the name to Chennai. It probably had been Chennai before it was called by the British Madras. But anyway, they went back to the old name. So if you can see it, depending on which map you look at, Chennai or Madras there. It's a pretty good sized city, fairly close to the beach. And we have good friends from India that are from Chennai or Madras. When we first met them, said they were from Madras. Now they say Chennai because that's what they call it now. But they had relatives who happened to be on the beach that day, and the tsunami warning was not very long because of the speed at which it traveled. And fortunately, all of them survived, but there were many, many people who did not. And if you think about an 8-story building coming in on a place where the ground doesn't rise very quickly, it can go quite a ways inland, creating a lot of damage. Okay. Now, let's get back to another issue, and this is tides. Now again, this book talked about tides more in the moon chapter than they do in this chapter. Okay, I think they had this slide in both places, if I remember correctly, because it seems like we talked about them earlier. But the tides are produced by the Earth-Moon gravitational attractions described back in chapter whatever that was, 16 I think it was. The basic pattern, you have 2 high tides and 2 low tides about every 24 hours and 50 minutes. Just a little bit more than a day length. So that means on some days, very rarely, you may only have 1 high tide. One occurs shortly after midnight, early in the morning, but the next one will be shortly a little bit before midnight on the next day. Did I say it right? No, I did it backwards. If it occurred just before midnight one day and you didn't have one at midnight, then the next midnight it comes right about right before midnight. So you may only have 1 either high or low tide, but most days, just about every day, we'll have 1 high tide, 2 high tides and 2 low tides. Okay. Now these tides can produce some strong reversing tidal currents in narrow bays, and they'll sometimes call those a tidal bore. That's a wave moving rapidly up a bay as the high tide is coming in. Now, I believe I've read this about the Thames River, and that's a river in England that goes right past London. London is quite a good little distance inland from the North Sea or whatever it dumps into, but it's close enough that a high tide in the North Sea will make its way up, and you'll see the tide come in London, and you'll see it go back out. So a tidal bore is a wave moving rapidly up a bay or river as the tide rises. A high tide is rising. So, not going to go into great detail, but just that mention. I can't both of these things, tsunamis and tides, are not mentioned as much in this book as they were on the slide set. Okay, so let's move, but they didn't mention tidal bore before, I don't think, in the book. Maybe they did, but you can go back and check. All right, so let's move to ocean currents. This is on page 624 in the big book, or 2419. Okay. What an ocean current is well, this is a strange sort of concept. It's kind of like a stream would be on land, except it's in the water. Okay? So here's a stream that's transporting water over large oceanic distances along roughly the same path constantly. So here you have a stream, or maybe even think of it as a river inside the ocean that's moving water constantly, roughly along the same path constantly, produced by two different effects. Now the first one I can see in some ways: density differences in seawater. Now most of the density differences are going to become as a result of temperature differences, because any fluid, whether it's a liquid or a gas, when it heats up, the molecules tend to move a little further apart, and when it cools, they tend to get closer together. They bounce off each other with less energy and colder, more energy and hotter, so they move further apart. That's the major cause of the density difference. Now they can be compounded a little bit by things like salinity, but usually that doesn't create that much of a density difference. Mostly it's caused by temperature differences. So, excuse me. My throat has been giving me a lot of problems today. Sorry about that. Okay, so there's one effect, density differences. The second effect is winds blowing persistently in the same direction over long periods of time. Now you might say, wait a minute, I thought winds caused waves. Yes, they do. They definitely do. But if you have prevailing winds that blow persistently in the same direction, that motion can go deeper and actually create currents that are deeper movements of water. But these will usually be, your density differences will be more in depth and go much deeper. The wind blowing will be currents that stay near the surface. That's a generalization. So let's look at those density currents first. The denser water displaces less dense water in the deeper basins. It's a lot like what we call the stack effect in temperatures. Warm air rises, cold air comes underneath. We saw it in weather, we saw it lots of places. That's what happens, okay? The denser water displaces less denser water, and especially in the deeper basins. The denser water goes down there, pushing the less dense water up. Now, there's three influences here. Like I said, the major one is temperature, water temperature. Polar water, of course, is colder. And if it's colder, it's denser. The water in the tropics is warmer and less dense. So here you have polar water coming from the north or very far south. Let's say in the northern hemisphere. From the north coming in, and maybe it's shallow up there but very cold, but then you hit a deep part of the ocean, it's going to sink and go down and push the warmer waters up. Okay? Warmer water in the tropics, however, tends to rise, and then if colder water comes in, they tend to move over and under. Okay. Now the next graphic we see is going to be absolutely, I find, amazing. I think this is the one. Yes. And I cannot believe, I find this really hard to believe. Here we have that cold, dense Arctic water. Now remember, Greenland's here, Iceland's here. Iceland's a volcanic island that just happened to come to the surface here. That's what islands are. This is not very deep water here, but it's very cold water. And once it passes that sort of ridge of land, you might say, between Greenland and Iceland, it sinks. And it sinks big time because of its cold. Now, this is the part that I can make sense of. 65 degrees north, you're really close to being at the Arctic Circle. That's 66.5 degrees north. So yeah, you're pretty close to the Arctic Circle here. Okay, that's cold, dense water. Here is 30 degrees north. That's about where we live. We're at 33, or so. Look at this. They are saying Antarctic water has made its way that far north. Way deep because it's so cold and dense, and your tropical water, your warmer water, is all up here. Now that's creating some currents that I don't even want to get into. And like I say, and the book has said, we don't understand but beans about the ocean. If this is truly a phenomenon that you see, what in the world is driving that? That's just hard to imagine that Antarctic water could make its way as far as 30 degrees north. That's amazing. So there's water temperature. We know the mechanism that it follows. The degree of that's is unbelievable. Okay? The second of these density influencers is salinity. Salt accumulation mechanism. Well, number one, when you freeze water near the poles, okay, it's fresh water that gets frozen. There may be little bits of salt trapped in there, but not much. So your water has more dissolved solids in it, which makes it a little denser. So freezing water near the poles, not just the coldness, but now the salinity makes it denser as well. Come back, okay? But another thing that happens is evaporation, okay? In the warm pockets, say in the Mediterranean Sea. It's pretty warm there, so water's evaporated. Well, that's pure water. That's H2O, not salts that get evaporated, so the water underneath that tends to get a little denser. Of course, it's warmer, so it gets less dense, but it's more salinity, so it tends to move in the other direction. Usually the temperature wins. Okay. Now, but you have that. Now, the other issue happening, you have runoff coming in every river that dumps into the sea, the ocean, whatever it is. That's mostly fresh water coming in. And if the fresh water is coming in, that means you're reducing the salinity because fresh water is mixing with salt water, and now it's less dense. Okay? So your density currents are really confused here. Temperature is the biggest change, and salinity can be affected in several ways. Now, the other thing that we have happening is suspended sediments. Okay? This produced turbidity, which is cloudiness, and those currents to ocean basins. Now, the more stuff you have suspended makes it a little denser too. And this is especially bad if, say, you've had a lot of flooding and runoff, say in the Mississippi River Basin. If you think about how big that Mississippi watershed is, lots of things. If they were getting dumped with heavy rainfall, which has happened, then you get more stuff being transported, not just salts, sediments. And that turbidity makes its way down to the Gulf of Mexico, and that produces denser water. Okay, so these things interact with each other in crazy ways, because usually that fresh water from the land will typically be a little bit cooler than the water in the Gulf of Mexico because it's further south. So lots of different things could be going on. Those are your density currents. Let's talk about the surface currents. Those are the ones, remember, the density currents are deep. Can be somewhat shallow sometimes, but they're quite often the deep currents. Your surface currents are your ones that are more affected by wind. The global circulation patterns maintained basically by patterns of prevailing wind. Now, I don't think that's everything about it, but at least that's the biggest contributor. Here's the other parts, also influenced by the rotation of the Earth and the ocean basin shapes. If you have some real deep places in the ocean, then sure enough, the water's going to go down into those, and you're going to have the shape of the ocean basin will also influence those currents. Okay, even the surface currents. Okay, wind is the largest. Now they have what they call, I don't even know how to pronounce this. It looks like it might be gyres, but I think they probably pronounce it gyres. I'm not sure, like gyroscope, but gyres. They're great systems of water circulation centered in the mid-latitudes. And when we see the graphic, let's go on and show the graphic. Here you see them, okay? In the Indian Ocean, they go around like this, okay? In the South Atlantic, they go around just about the same way. In the North Atlantic, they go in the opposite direction. Now that's largely because of the Earth's spin and the Coriolis effect using water rather than air. In the Pacific, you have sort of a mixed bag. You have some gyre in the southern part, but the opposite gyre further north. Down here, it's pretty much a just like you saw in South Atlantic, the South Pacific follows that. The Indian Ocean, they follow that. But in the northern part of Pacific, it goes in the opposite direction. So great systems of water circulation centered in the mid-latitudes, and the direction is dictated by the Coriolis effect, which we saw with winds. We've seen in a couple of different situations. Okay. Now, let's look now at the, and by the way, density currents were on 624 or 2419. The surface currents, the last slide, was 2420 or 625. Flipping over to 24.3, we're going to talk about the ocean floor. But here again, we run into a person in science, people behind the science, and this is a rather incredible lady here. I don't know if I can get the whole thing in here or not. Her name was Rachel Louise Carson, and she was born in 1907, which was fairly early in the century, 20th century, and lived till 1964. So only 57 years old or so when she died. But she was a U.S. biologist, conservationist, and campaigner. She raised a lot of interest and a lot of attention on some of the very things we're talking about. So a good read there. And I hope everybody's already chosen a paper topic. I hope you're already working on your papers. I hope most of you have turned them in already. I think the three of you have, but I'm talking to the rest of the crowd here. She would be a good source, a good person. This cannot be your source. The book cannot be. It can lead you to look at things, and even if you read this, you'll probably run into some other things that you might want to look at. Actually, fewer things here. They mentioned several books that she wrote. One was, I think, The Sea Around Us, published in the year of my birth, 1951. Her second book, The Edge of the Sea, in 55, when I was 4 years old. And her third one was, or her most famous book was The Silent Spring, and it was a very powerful indictment on the effects of chemical poisons, things that I was talking about earlier that we do. So anyway, any one of those books could be a good paper topic as well. All right, so let's get back. The ocean floor. Now the ocean floor, we probably don't understand too well, but there are things about it we do have a fairly decent comprehension of. So let me show you when they're talking about them. The continental shelf is basically an eroded continental margin. The likelihood is at one time or another that was part of the continent, but as the erosion occurred and kept washing away soil, now you leave a shelf there that was continent before, but now is eroded away, so now part of it is underwater. This is what that represents here. Now on our eastern seaboard, the Atlantic side of the U.S., the continental shelf can go out sometimes almost as far as your eye can see. Not quite that far, but it can go way out there. On the Pacific, no, it doesn't happen like that. This doesn't show it too well, but this shows a little more gradual fall off here, whereas on the Pacific side, it falls off much more quickly. Okay, so on the Atlantic side, we usually have a fairly long continental shelf. I've been in the ocean, like I said, in Virginia Beach, Virginia, and it seems like you could go out for 100 yards or more and sometimes actually find a sandbar out there, and you actually be out of the water or almost out of it, you know, and maybe you had to swim out to get to it. So the continental shelf can go. It's relatively shallow water. Relatively is the big word there. Could be 6 to 8 feet deep. It could be right near the surface. Then past that is the continental slope. That was probably the original boundary of the continent. Okay, that's the continental slope here. Much steeper, usually on the Pacific side. In fact, very steep sometimes there. Okay, there's another picture of a really steep slope. Okay, now it's a steeper transition feature beyond the continental shelf. It was probably pretty close to being the edge of the original continent. Now, it's often cut by submarine canyons. In other words, places where you've had a whole lot of erosion, and it's really erosion, and it's dug out parts of the seabed. Okay. Now, I also say this. They mention something here they don't mention over here. The continental rise. I'll give you my layman's view of what this is. Remember I said the continental shelf was where the soil eroded away? It made its way down here, and this continental rise is probably largely composed of the soil that eroded away from the continental shelf and deposited in the continental rise. Because the sea floor was probably originally fairly flat there, but when the soil came in, eroded off the thing. Now, if you had very strong currents coming out here, that would create the submarine canyons. Whereas a strong current in a river would cut something like the Grand Canyon on land. This would cut canyons in the ocean floor. Now, further out, you get what they call the ocean basin. That's the actual bottom of the ocean, way out in the deep. And these are, now they say the deepest part of the ocean. I tend to kind of disagree with that a little bit. The ocean basin is very deep, for sure, okay? And that's what they're sort of talking about here. Here they call it the abyssal plain. I don't know why they give that name. Here they say the ocean basin floor. Notice that it's very, very deep there, about 5 kilometers deep, which would be about 3 miles deep. That's pretty deep, okay? There again, the abyssal plain or the ocean basin floor. Now, the reason I didn't want to say the deepest part of the ocean, okay, no, let's back off. It's characterized by practically level abyssal plain, and that's what they call it here. They don't call it that here, but it is the abyssal plain here, sort of here and here. They just don't name it, okay? However, that abyssal plain can be interrupted by mountainous ridges, like here, seamounts under there. Now, what causes those? Not too sure. I would think it's probably volcanic activity. Whether it actually broke the surface, but remember in one chapter we talked about the batholiths and the dikes and those things. If this was happening underwater, the magma didn't actually break the surface, but it pushed things up. That could be your seamounts as well. Possibly folding or faulting of underwater basaltic layers in your oceanic crust. All the same things that happen on land could be happening down here. They're kind of muted because you got a heavier overburden here, the ocean, rather than just air above land. Okay. Now here's the part, and I guess this is where it comes true. The trenches occur along the ocean basin edges. Those are the deepest part, those trenches, okay? And they're at the ocean basin edges. And if you say, well, that's still part of the ocean basin, yeah, then this is true. But here are the trenches. This is where the oceanic crust subducts underneath the continental crust. Now that didn't happen over here. It's just eroding away here, but it is happening on this side. This is a converging plate boundary. This one is not. Okay. In fact, this is a diverging plate boundary. The same plate is under all this, and here is where it diverges, spreading apart. Okay. That's your mid-oceanic ridge. The Rift Valley is right in the middle of that. It's kind of the crater, you might think, of that volcanic activity there. Now, volcanic peaks form scattered seamounts. Those could be those seamounts. This is certainly a seamount. The Hawaiian Islands are. All of your chain islands, pretty much in Pacific or Atlantic, are these volcanic peaks and form those seamounts. When they break the surface, they become islands. When they're underwater, they are called seamounts. Okay. Now, here, they sort of stick this in here before they talk about it. But these, the light blue lines here, are your ridges where you have your, and I think that's an exaggeration there, but where you have your diverging plates, and the ridges form here. Mid-Atlantic ridge here, you have a Mid-Pacific ridge here, East Pacific ridge here. You have all these ridges, okay? Now, and again, they haven't got the slide here yet, but then you have the trenches here, the Puerto Rico Trench, the Middle America Trench, the Peru-Chile Trench, the New Hebrides Trench, the New Britain Trench, Sundra Trench, Mindanao Trench, okay, Marianas Trench. Now you can't see it, but there's a string of islands here called the Marianas Islands. Probably the best known of those, well, I think there's actually a couple of them that are fairly well known. One is called Mariana, the other is Guam, is in that chain of islands. That is the deepest part of the ocean anywhere, the Marianas Trench. Okay, you have a Japanese trench, a Kuni Trench, just a whole bunch of trenches. Aleutian Trench on the outskirts of the Aleutian Island, Arc Island chain. So those are some of your trenches. They mention trenches here, and they kind of mention in the earlier slide the ridges. Okay, but that's what they're getting at here. Oh my goodness, that was the last slide in the chapter. Okay, I say it every chapter, and this one is among the most to say it. Nothing replaces reading the book. Now, this chapter has, to me, a fairly short summary. Okay, has a lot of italicized words, which are the most important to pay attention to. Most of those occur in the key terms that you see on the right-hand column of that last page. And the key terms are listed alphabetically, but they do give page numbers where they're either first described or defined or mentioned. But then applying the concepts. I think the best thing to use to study for your test, and you don't have a lot of time to, but do it. There are 46, which is probably a few fewer than normal, but 46 multiple choice questions, answers provided, well worth your looking at. Questions for thought, only 13, that's a few fewer than normal. But for further analysis is 6, which is maybe on the upper side of what they usually are. The other group, the parallel exercises, they are more like those examples in the book, and that's up to you whether you want to pursue those or not. But that ends chapter 24. That ends the term. Now, y'all have been a remarkable group because we were cheated out of about a week and a half of our term. It was supposed to be a 10-week term. It turned out to be an 8.5-week term. And the Monday, Wednesday classes were cheated out of another. Whoa, here comes somebody. Nakaya is here. Good. I'm glad she made it. Okay. Let me get Nakaya here. Okay. And the fact that we've been able to finish the full term is pretty remarkable. Y'all have been real troopers to put up with my racing through this trying to get everything covered. Okay. Now, any questions on chapter 24? Nakaya, we just finished the PowerPoint show and the lecture, that kind of stuff. We're getting ready to go into our lab now, even though we're not quite at lab time. Are we, Valerie? We have 4 minutes, yes, okay, but we'll get started early. I don't think the lab will take us the full 2 hours, but we'll use as much of it as you feel like you need to have. So, any questions on chapter 24? Oh, absolutely. Why don't we do that? I'll stop the recorder here. I want to get up and stretch my legs, mostly my knee. My knee gets really stiff when I sit too long. So I think that's an excellent suggestion. So, all right, we're getting ready to start the lab, Laboratory 9, Earth's Waters. And I sent it to you on Blackboard Message. Now, there's a lot of things on Blackboard Message, so you have to look. It's called Lab 9 or Chapter 24 Lab. I prefaced my remarks by trying to get, I may not have said Lab 9. Lab 9 is listed on the file name, but Chapter 24 Lab is in the verbiage that I wrote about it. Okay. Do all of you have that or at least have access to it? Yay or nay? Okay. The first thing said, name the 3 major watersheds in the continental U.S. Okay. Now, not Canada, continental U.S. My slideshow is not moving. Okay. Whoa. If you're in the book, this is long about page 610 or 24-5. That picture is much better than one on the slide set, but you can see it here. I'm not going to call out the answers, but y'all can work as a team and help each other out if you want to. Or you can be silent. I don't care. Anybody have a question about the 3 major watersheds in the continental U.S.? Not hearing anything. So I hope you got them. Do you? Ready for the next slide?
Yes.
Okay. Y'all can talk among yourselves. I don't mind overhearing. I'm not going to give you the answers though, but I'm showing you the answers. Okay. Question number 2. Name the 3 largest oceans on the Earth, not just U.S., on the Earth, and list two continents now that border each of them. Okay. Okay, there's a visual that at least lists those three oceans. I'm not going to say what they are, but I hope y'all can read them. But please pay attention to what the continents are. Now, they don't list those on this map, but I'm hoping you know what they are. Okay, does anyone know what this continent right here is? Can you see my arrow? North America. What's this one down here? South America. What's this one over here? Come on, you geography people. What continent is this? Come on. Are y'all just being shy? What continent is this? Anybody? Make a guess. Africa. What continent is up here? Okay, Asia's over here. This would be Europe on this side. Now, they're all one big continent, but yeah, this is usually called Europe. This is called Asia. Okay? And then this, I guess they count a continent, though it's the smallest one. Australia, you got it. So you pick the oceans and name two continents that border that ocean. Now, this ocean you see here and here because it's such a big one, and just any two continents that border this ocean, that ocean, and this ocean. You have more than two on every circumstance. So you pick the ones, and when you're ready for me to change slides, I'll change slides. So let me know when you're through. Okay, most of the rest of you. All right, now I didn't mention one, and it was mostly because this block was in the way. I'm wait till it fades out. I guess you could consider this a continent down here too. As soon as that block fades out, that I can't get it to fade out. Fade out block. Okay, there it goes. What's this down here called? It's not this big. It just looks big on this drawing. What is that called? It's probably smaller than Australia. I don't know that for sure, but I'm guessing it is. Anyone know what it's called? Antarctica, you got it. So if you wanted to call that a continent, you could. It's, maybe, but there's only two of them like this. Australia is a continent, but it's also a country. And Antarctica isn't really a country. It doesn't have a government or anything else, but you could consider it a country as well. But these continents, these other continents, are made up of many, 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 many countries. Two exceptions are Australia is one country, and Antarctica you can call a country, but it's really not a functioning country. So with that in mind, question number 3 is not asking for continents, it's asking for countries. And it asks for 1, 2, 3, 4, 5, 6, 7, 8 seas. And I can see 1, 2, 3, 4, 5, 6, 7, 8 seas listed on this globe. There are many other seas that they didn't list. In fact, over here, they list another sea that's not listed on the globe. So if you could do that. Here's another sea that's not listed on the globe, but is a sea. But you'll need to know where they are, and then just pick a country that borders, okay, list the sea and at least one country that borders that sea. Now, some of you may not know quite so well some of these, okay? You should know this one. This I sort of gave away, and that one I gave away. This one's pretty obvious, I hope. Mediterranean, you can probably pick several countries there you could choose. I think you know where the one here, Gulf of Mexico, is. You can pick 1 or 2 or 3 or 4 countries there that you could name. What I'm not sure if you know the countries around this one, okay, or especially that one. If you need help with that, feel free to get a book, a globe, go to the internet any way you want to. And this sea up here that you see, it borders a whole bunch of countries up here. So you can pick a whole series of those, and hopefully you'll know some. So please let me know if you have any doubt, and I won't tell you the name, but I'll indicate whether you got it right or not. Is that okay? So list at least 8 seas. You see 8 seas listed on here, and you see 2 more seas listed here. And if you know of other seas, there are plenty of other seas, and when we talked about them in class, I mentioned some of those. So any of the seas that you're familiar with, you can list, but you'll need to know what country they border. And if you have doubts, please ask me, okay? And we'll talk about it. And let me know when you've got this one completed. Wow, quick. Any of the rest of you need a little more time? Any of you uncertain about a country? Because no countries are listed here, you just have to know them. Anyone have a country question? Okay, if not, we'll move on to 10 of the ocean currents and list an ocean with which each is associated. There's 6 at the bottom, no, 5 at the bottom of the first page, 5 at the top of the next page. Okay, so let's see if we can find the slide that lists the currents. Getting closer, there it is. 2 types of currents. Ah, there it is. Now if you got a book, I didn't say on the other one, that last slide that we were looking at that you got both the oceans and the seas off of, that was on page 618. Same picture, but it's just bigger that you're able to read better. That's on 2413. The one we're dealing with now is on page 625 or 24-20. Okay, easier to read from your book, but if you don't have a book, hopefully you can read from here. So we want the currents. The currents are the blue lines here. Okay, and there's a bunch of them. There's 10 that you're looking for, any of these 10. Now you'll need to know in which ocean they're associated. Now some of them may have a variety, okay, and you can either choose an ocean or, oh wait, here's Harry. Harry, welcome. I didn't see you there. Okay, Harry, you in place?
I'm in.
Okay, good deal. Um, have you looked at Blackboard message recently?
As of
Oh, you
yes,
you got the lab?
I got the lab and I have the homework.
Okay, yeah, but do you have the lab that I've just put out there on
Yeah, lab 8.
no lab 9?
Oh wow. Give me
Yeah,
a second.
yeah. I just put it out about 2 3 hours ago.
Okay. No, I do not have that. I can print that off.
Okay, that's what we're working on now.
Okay. Let me not hold up the class. I'm gonna go ahead and print it out.
Well, we got plenty of time.
All right.
There's so much stuff out there, it's maybe hard to find, but it's there. The verbiage I say on it, say the Chapter 24 lab, the actual lab title has L9 at the end of it, meaning lab 9. 2 pages.
Here it is.
Okay.
Okay, gotcha. Print. Ready. All right, I got it.
Alrighty. Okay. Now we're already on page 2, but let me go back quickly on page 1. Do you have a book? Uh, is it the big thick book or is it a little thin book? Huh?
It's the big thick book.
Okay. Question number 1 on the first page, you can find on page 610. Since we all did this, I'll give you the same benefit they had. That's there on the graphic on page 610. Question number 2, you can find on a graphic on page 618. Now, at least you can find part of it. The continents aren't, they're shown, but they're not listed the names of them. So if you have any question on what the name of those continents are, feel free to ask. Okay? Uh, or you can go back to the YouTube video. Now, it's going to be a while before it gets out there, but when the YouTube video gets published, then you can go back in here, and I named each one of those continents. Okay? Then number 3 is on that same page, same graphic. The 8 different seas are listed. And if you do pay attention to the YouTube video, I point out that 2 other seas are listed on the same PowerPoint slide. And so now, countries aren't listed here, so you'll have to know enough about the countries, but use a globe, use an atlas, use something, or ask questions. Okay? And remember, this is a lab. You can work with one another. So if some of you want to help Harry out, you can do that as well. Okay, that was questions 3 and 4. We're just getting ready to do, no, I'm sorry, that was questions 2 and 3. Question 4 was the one, so we're at bottom of page 1, top of page 2, the currents. And that's the one you see on the graph on the slide here. And this is page 625 in your text. Easier to read in your text, but you can read it, I think, adequately here too. It says name 10 of the ocean currents and list an ocean, only one, in which each is associated. Now some of these are listed basically in all 3 oceans. I can see one that's like that. So just pick one of the oceans and list. Or a lot of them are only in one ocean, and then pick that ocean and list it. And I know that Valerie is probably already through with this, aren't you, Valerie?
Halfway.
Oh, halfway. Okay, good. I figured while I was doing all that yakking, you already finished. Okay. Now again.
I've dissected all of my diagrams, of course.
Oh, okay. And by the way, y'all can talk among yourselves. I don't object to this. If this was a lab in a class, you'd all be working together, or as many as you wanted to, or you could work individually. It doesn't matter. So feel free to talk, ask, run things by each other. Ask me. I'll be glad to answer. But I'm not going to give you an answer without any, except showing it to you right there on the screen and telling you which page in the book.
Question.
Yes.
When you mentioned on the last one, you said continents and I guess the country.
Right. 2 and 3.
Of the 7 continents.
Okay. Let me go back to the figure. Whoops. This thing won't move sometimes. Okay. Yeah, that's why I said that. So you would ask the question if you needed it. Okay, here's the one. Okay. Now ask the class to participate again. What continent is this one where my arrow is?
North America.
Got it. This one?
South America.
Got it. This one?
Africa.
Got it. This one here, you can't see a division, but it's right here. Say again?
Europe.
Europe. This over here.
Asia.
Asia. This down here.
It's not really called Australia, but Australia.
No, it is. It's both a continent and a country. It's a country and a continent. Okay? This one down here that is partially being blocked by that rectangle, but hopefully that's Antarctica. Now that's actually not a country. There's no government or anything else there, but you can consider that either a continent or a country. Same with Australia. Okay, so in question number 2, I want the continent name, and you have multiple continents you can choose. Pick any 2, and then in the number 3, the seas, the major seas, which you also see on this thing, pick a country near that sea. And here's what I was talking about. They named 2 other seas over here in the verbiage that are not listed on the globe, on the map. So you could use either one of those 2 as well, but you'd have to pick a country, not a continent, a country that borders those 2 seas as well, or any of these seas you see here. Okay. Now, ready to go back to currents?
Yes, sir.
Okay. Oops, went right past it. Okay. Now, this is also in the book, as I said, on page 625. Much easier to read in the book than it is here, but this is asking for a current, and you have bunches and bunches of currents listed here. Pick any 10 of them, 5 on page 1 and 5 on page 2, and then list one of the oceans, an ocean in which each is associated. Okay, so some of them actually span more than one ocean, but you can pick any ocean that current is found in. And these are the blue lines. Some of them don't have names by them, but you have plenty that do. Now don't think, here is one over here that's the same as this one over here, but there's in another ocean it has the same name, but it's in a different ocean. This ocean and that ocean are the same, that the big ocean, and this is a same name but in a different ocean. So yeah, things like that. This one down here is in all three oceans. Okay, so just to let you know that. But you can pick any one, and not all of them are called always currents. There's one here that has a different name, and that's probably the one most known to us. Okay. The Gulf Stream was one I was talking about. It doesn't actually have current in its name, but it's definitely a major current. And then the others always have, yeah, this one, current is still in the name, though it's not its own word. Okay. Okay, when you get all 10 of those with just one ocean for each, let me know when you're through. Okay, this one right? Okay. Okay. I don't see a name for it. You have that from another source?
No, I'm asking, is that part of the
Okay. You can, yeah, you can find, is that the name you're trying to say?
Yes.
Okay. I think that's it right there. That's the Benguela or something like that. I think that's it right there.
Next to it is actually part of the South Equatorial current.
Okay, that would be this one up here. That's South Equatorial, meaning it's near the equator. See, this is a long way from the equator, so that wouldn't be. Now, these all make a gyre. We talked about that in class, but there's at least 4 different currents that make up one gyre. Okay, so yeah, don't think that's all one current. Gulf Stream has part of it's here, part of it's there, and part of it's there. In fact, it actually goes up here. So Gulf Stream has several blue lines with it, but most of them are listed just, there's only usually one line per current, except something like this one down here that's listed 3 different times. That's one current, but it just goes all the way around there. So most of the rest are just one line per current. I think. Correct me if you see any others that are multiple. Gulf Stream is definitely multiple. And when you are through, let me know. I forgot to turn on my light again. I'll try to do it without wrecking my system here. Okay, everybody's through with the currents. You would have to pick right after I put 2 goldfish in my mouth, but I'll chew them in a hurry. Okay, number 5 on page 2. Let's find the slide for that. There we go. Now, unfortunately, I have this stupid window that is blocking that for most of you, isn't it? But if you got a book, this is on page 627. Okay. Now, Roy, sorry about the block. It's getting in your way, but pick up what you can on the outside. Now, this is both number 5 and 6. 5 is asking for the ridges. Those are the sort of aquamarine or light blue type lines. Your trenches are the dark blue lines. Okay, you see the difference? The light blue lines are your ridges, the dark blue lines are your trenches. Okay, the name that you see near them will list which they are, and then you pick out the ocean that they belong in. There's a couple without names, so don't worry about those. Pick ones that have names. 4 ridges, 12 trenches. Roy, if that rectangle is in your way too much, talk among yourselves and help Roy out. He doesn't have a book. Roy. Nakaya must have had to leave, but she's back. Oh, and it's time to call roll, and nobody told me that, did they, Valerie? Falling down on the job. Okay, Don hasn't made it in today yet. Capri hasn't made it in today yet. Bridget hasn't made it in today yet. Nakaya just came back, so she's here. Thomas doesn't make it in today yet. Juan hasn't made it in today yet. Scott's still here, I believe, aren't you? Yeah, I see Scott. Patrick didn't make it in today yet. Caitlin hasn't made it in today yet. Parisha hasn't made it in today yet. Harry is here. Cormisha hasn't made it in today yet. Rod hasn't made it in today yet. Jacob hasn't made it in today yet. David hasn't made it in today yet. Leon hasn't made it in. Roy's still here. And Valerie, I think, is kind of here. Okay. Good deal. 1, 2, 3, 4, 5. Is that all? 1, 2, 3, 4, 5. Is that all I got? Yep. 6 students and me. If you have any questions at all on any of these, feel free to ask, but also talk among yourselves. Was there a question? Okay. Okay, that is Lab 9. Are there any questions about it? Okay. Question number 5. What about it?
Pretty much everything. Yeah, everything listed is so there are other bridges and trenches. These are just the large ones.
Well, um, I see one down here. Because of the box you may not be able to see it. I don't see a name on it. So you know there's one, but it hasn't got a name. This one right here, now that the thing's fading out, that doesn't have a name. Now it's looked like it was part of the mid-Atlantic, but that's no longer Atlantic here, okay? So yeah, there are trenches that may not have names, but those are the bulk of your trenches. Some of them are being hidden by the box, so I can't see. I'm sorry, ridges, the light blue ridges. The trenches are here, and you see there's more than 12 listed. You have to look for them sometimes to find them. And it's sort of interesting to note the major ridge is here in this ocean, okay? That's where most of the spreading is happening, but that's not the only place. Everywhere you see a ridge, there's some spreading going on, okay? For instance, this one here is the reason we have that island chain that's our 50th state, okay? There is a ridge right there, and those islands make up the ones that broke through the surface of the ocean. I think on further north from there, you probably also have Midway, I believe, is in that same ridge, and possibly Wake. I don't remember where Wake is especially, but I think it may be in that same chain. But it's a long way from the islands we know the best. Okay, so there probably are others, but there aren't that many ridges. There are tons of trenches, and most of them are located in the big ocean. Number one, because it's so big, but number two, that's where the crunching is going on. The spreading's going on in the Atlantic. The crunching, the converging plates, are happening more in the Pacific. So that's why you see the trenches here in the big ocean and not that many trenches but one really big ridge in our ocean here where we live. So yeah, this probably is all of them, but these are the ones. I think the way I phrased it was the larger ridges and larger trenches. I figured that's what they chose them from. Let me see what the book says. Yeah, if you notice in the book on page 627, the location of some of the larger ridges and trenches on the Earth of the Earth's ocean floor. That's where I got the idea larger. And pick the ones that are named. Pick among those that are named. Any other questions? Excellent question.
The ridges are the purple.
Yeah, no, wait. The trenches are the dark blue or purple, yeah. And the light aquamarine or light blue, those are the ridges. I may have said them backwards at some point, but that's what they are. You can tell by down here. The trenches are the dark, the ridges are the light. Okay. I'll leave this up here and I'll be available for as long as you have questions. Now, just to give you an idea, especially since Harry and possibly Nikaya came in after I first said it, let me say this again. After class today, I will be posting out there the Chapter 24 test, which is Test 9, and I'll also be posting the final exam. Okay, Chapter 24 test is, I think, 2 pages, final exam 1 page. Now, depending on your printer, it may spill over onto another page or something like that, either one of them. But those, try to get everything that you can into me. That includes your research paper, just as soon as possible. Any of the old labs, earlier tests, all that stuff as soon as possible. Okay, the stuff that we've had today, this lab, the Chapter 24 test, and the final exam, when you get it finished, send it to me. Don't wait and send me a whole bunch of stuff at once. Get it to me as soon as you can. Now, if you're working on them at a place you can't send, you get 3 things finished, then send them when you can. But I'd rather have them as you finish them so I can grade them as closely to that as I can. I've showed the others this earlier. Most of what I'm showing here I printed off since the weekend. Not all of it, but most of it. And there's still stuff out there to print. Harry, I was printing some of your stuff when I had to stop and teach my first class today, so I didn't get all yours printed. Stuff that you sent quite a few weeks ago. And then I know that people have sent stuff since I've been teaching today, because I started teaching at 11:30 and I'm going till almost 5 o'clock now. So I know some people have sent stuff in this time frame. So I've got lots more printing to do. Not as much as I did have, but lots more. And then I've got tons and tons and tons of grading to do. So I'll be working on that as heavily and quickly as I can. I have 3 classes tomorrow, separated by a couple of hours, maybe close to... Okay, wait a minute. Here's Cormisha. Fantastic. Cormisha's here today. Okay. Gotta find you. There you are. Okay, Cormisha, are you within earshot now?
Yes, sir.
Okay. We've just finished doing the Chapter 24 lab. That's lab 9. I don't know if you had a chance to print it off the Blackboard message yet. Were you able to do that?
No, sir, but I can go pull it up right now.
Okay. Now, if you go and listen, now it's going to take a while for this class to get loaded onto Blackboard. Loaded onto YouTube video so you can access it through Blackboard. So if you get that printed, I'll go over fairly quickly with you where you can find the answers, because I've done that for the people who were here. I'll do it for you since you came in.
Yes, sir.
The other folks that didn't show up today, which is the vast majority, they're going to have to wait and listen to the YouTube video, and then they'll see everything they need to see. And you may need to wait and listen to it to get all the details, but I'll try to...
I'll do it. You gonna upload it like after class?
Yeah, but it takes a while. It takes about, I'd say, 2 or 3 hours for it to upload itself onto YouTube, YouTube, and then I still got to move it to the playlist. So,
As long as I get it to you by tomorrow, that'll be fine.
oh goodness, yes, tomorrow will be fantastic. You can either get it to me on Friday or Saturday, but the very latest, and this is what I wanted to say in front of Harry and everybody, Nikaya, who came in sort of later too. I've got to have everything in by Sunday, and in time on Sunday for me to grade it. So 10 o'clock at night is not in time for me to grade it. So if you can get it to me, I'd say by noon on Sunday, or no later than 3 o'clock on Sunday, that would be really, really good. But don't wait till then. If you can get it to me sooner, like Cormisha said, if you can get it to me tomorrow, oh, that's wonderful. Okay. Friday would be all right, Saturday all right, Sunday in time for me to grade, because I have to have grades entered in the system before noon on Monday. So don't wait until Monday morning to get it to me. It's almost going to be impossible for me to get things graded, put on Blackboard, averages calculated, and put the grades out there if I don't get them until Monday or late Sunday. That's going to be hard to do. So try to get me as much as you can. Hopefully most of you have turned in your research papers already, and most of you I hope have turned in your earlier quizzes, labs and tests. Just the things we've done this week. Some people have already turned in the test 8 and labs 8 that we did on Monday. Thank you for getting those in. The rest of you, get in as much as you can, as soon as you can, and try to get everything wrapped up by midday Sunday if possible. Okay? Now, if you can't possibly do it, still get it to me. Yeah, I may have to give you an incomplete, but don't linger. Go on and get it to me. Now, what I really fear is I've had a bunch of people who I haven't seen literally in weeks. Okay? I don't know what they're doing. I don't know if they're going to finish the course or not, but believe it or not, there's some people who have not turned in the first thing of anything. And that's disheartening to me, okay? And it could easily be I'm going to start getting piles and piles of stuff in right at the end, and that's going to be really disheartening to me because that really piles it up on me. But I'll get done as much as I can, as soon as I can. But if I don't have everything in by noon and graded and stuff by noon on Monday, it's going to be an incomplete. But as soon as I get the grading done, I'll change that I to a letter grade. Okay. I just had an email today from a student I had last fall that he hadn't gotten everything in. I held off and gave him an incomplete. I think he finally got one or two more things in, but it was only enough to get a D. I gave him a D, and then he said he looked at his grades and saw he had an F. I didn't give him an F. Okay, but he was saying he failed the course. Now, maybe a D was failing. I don't think so, but don't be in that boat because things done last fall, it's way too late to change them. So this is not for you guys. You guys are getting things in on time. It's for ones, hopefully, who are going to be listening to this later saying, hey, I got to get a big move on, really rapidly. Okay. So, Cormisha, and I know Harry has, I believe, I didn't ask, Nikaya, did you get the lab printed? I don't know if Nikaya can hear me.
Yes, sir.
Okay, so you're on top of the lab. Okay. Cormisha, did you get yours printed? She may still.
No, sir, but I got it pulled up.
Okay, so you see what it's like. So
Yes,
let me. Are you looking at the YouTube now, or are you looking at it? I don't know if you can see them both at once.
The lab itself.
Okay. Do you have a book?
No, sir.
Oh, you don't? Okay. Well, so you right now have to either choose to look at the lab, or you choose to look at the YouTube video. I mean, not YouTube video, the Zoom screen. But which you want to look at?
The Zoom screen is fine.
Okay, I'm going back, if I can get Zoom to move, the PowerPoint to move. I'm going to go back and point out to you okay. Question number 1 can be found right there. if you had a book, and you're welcome to communicate with these other folks in the class. This is a lab. You can work together. But question number 1 is found on that screen right there. And I've stopped and we did this. I've done it now I think about 3 times now, so you can see it on the YouTube video. Okay?
Yes, sir.
All right.
Miss Valerie gonna help me.
Okay. All right.
She has a book at home.
Right. Okay. Well, then that's where you'll see question 1. Now, yeah, here is where you'll see question 2. I'm coming to it. Oops, went right past it. There's question 2. Now, the thing that's not on this, it's on it, but it's not named, are the continents. And since I went through this with everybody, I'll do it with you too, but Valerie can help you too. This is North America here, South America there, Africa here, Europe is this little bit here, Asia is this huge bit here, Australia is both a continent and a country, and Antarctica is a continent. It's not really a country, but you can name it as a country if you want to. It doesn't have a government or anything like that, but you can treat it either as a continent or a country. So that's where you'll get question number 2. Okay, that's also where you'll get question number 3. Here are the seas listed here. Okay, and over here on the slide, you'll see 2 other seas listed that aren't listed on the map. But I think you know where they are, but if you don't, you can look them up on another map. But the seas that are listed. Now what you have to list with these are the countries they border. And I think you can figure out the country this one borders. And remember, you can name that either a country or a continent that borders and this borders. There's a bunch of countries that are on here. You can pick out any one of them. There's several countries on that sea, and I'll let you choose. You can get a better map if you want to. Also, this sea doesn't list a country, but you'll need to find it. This sea is pretty obvious what country borders it, but that's just one of several. And let's see, we named some other seas. Oh, here's one up here that borders a whole bunch of countries. Okay, so I'll let you figure that. So that's number 3. Okay, 2 and 3 are found on that slide, and it'll be out there on the YouTube video as well when it finally gets posted. Okay, now
Yes, sir.
questions number 4. And Valerie has all this stuff. Okay, here's question number 4. These are the ocean currents. The ones that are named here, those are the currents, and you list which ocean they live in. Okay? Some currents are not named, so don't worry with those, but those that have names, those are the ones that you can list. And there's way more names than you have. You only have 10. 5 on the first page and 5 on the second page. Okay, so pick any 10 and name which ocean they're in. Okay, so that's question number 4. Bottom of page 1, top of page 2. Then questions 5 and 6 are both listed on this next one. There they are. Okay, now I could give you the page number in the book, but you don't have a book, so I won't bother with that. The light blue are your ridges. You see the thing down here. Some of them are not named, but the ones that are named, you can pick those out and name those. They only ask for 4 and say which ocean they're in. Okay, the trenches are in the dark blue or purple. Okay, and there's a bunch of them listed, some named and some unnamed. Only list, I think it said 12 of the larger trenches that are named, and you can find the name of at least 12. I think you can find more than that. And which ocean they're in. And that's the lab. That's the lab for today. All right, and you think you can work it out?
Yes, sir.
Okay, does anyone else need any more time, have any more questions? I'll be glad to answer them, but the sooner I get off the sooner I can put your Chapter 24 test, that's test 9, and the final exam out there on YouTube video. I mean, not you, on Blackboard message. And I'll get them out there just as soon as I can after I wrap up class. It takes me a little while to get class wrapped up. I've got a lot of things to close and make sure everything's in order. So, any further questions? I kind of hate to end early today because we only have 1, 2, 3, 4, 5, 6 people that have shown up, period. And since a few of you did come in late, I'm afraid a few more will be coming in. And if I shut down, I won't be here to notice they came in. But they can watch it on YouTube video and get all the answers. Okay, so what you think? Anyone need more time? You need to talk with each other some? That's perfectly fine to do so. Anybody? One more thing, I think I mentioned it early, but several people have joined since then. Finally, like in the last couple of days, they finally opened the student course evaluations, also called surveys. Okay, they're asking everybody to do them. They gave us 1 day for each class to make the announcement. So I'm making the announcement for today's classes. Monday, Wednesday classes today, and Tuesday, Thursday classes, I'll make that tomorrow. I did see them in time to make it to some classes yesterday, but not in time for everybody. So this is not the best way to do it, but please do the student course evaluation. I think they'll give you at least a week or so to do them, so please get those done before you shut down for summer. Okay? Now, I'm almost guarantee you they're not going to be open past the end of this month, because I'm pretty sure they feed into the old system. If they have any connection at all, it's in the old system, and we're going in the first of next month, 1st of August, we're going to be completely on the new system, which is called Banner. So I don't know that they'll keep it open past the 1st of the month. So please get it done sooner rather than later. Student course evaluation. Go to your email. There'll be a link that you go click on the link. It takes you straight to the thing. Please do them. I heard estimates of anywhere from 5 to 15 minutes is about all it'll take to do those student course evaluations. So please do those. All right. Any questions, comments, last shots? I'll be glad to stay on just as long as you need me to be on here. But on the other hand, the sooner I get off, the sooner I can get your last test and final exam out there for you. So what's your pleasure? Any questions? All right. So all the comments I'm either hearing or not hearing, it sounds like I ought to shut it down. If anyone has an objection to that, please let me know, and I won't shut it down until I clear all your issues. Okay, I hear none, so I'm going to stop sharing now. I'm tired of sharing. Okay, and I will end the session. I've enjoyed having y'all, especially you guys. You're the faithful, the few, the proud, you know. But many other good ones in here too. They're just not here today. I don't know where they are. But I've appreciated having you in class, and get me the stuff as soon as you can. So unless there's any last thoughts, parting shots, I'll end the meeting. Bye-bye all.